All right. I know everybody's at home. They did cancel class tonight, but I wanted to at least get the recording out so you have this information because I'm not going to be able to really push back everything even more. So we'll be able to go through this, and I'll go through a little bit more of what 5.3 and 5.4 is on Thursday at the beginning of class. It's not going to cover it completely because you can watch the video and get the notes and stuff online. So last week on Thursday, we talked about addition and the addition rules of probability. Today, we're going to look at the multiplication rules of point of two events and if they're independent or not. So when we're looking at events in addition, we were looking at if they are mutually exclusive or if they basically were separated. So with multiplication, we're looking at if their two events are independent or not. If two events are independent, that means the probability of the first event doesn't affect the probability of the second event. When two events are dependent, they do impact each other. So a great example of this would be, as we talked about last week, flipping a coin and rolling a die. They have no impact on each other. So those two events are independent of each other. However, if we took a playing card out, we took a king out of a deck of playing cards, and then I set it aside and I picked another one out, the probability that I'm going to draw another king has changed. Therefore, those two events would be dependent. So that's really what we mean by independent and dependent events. Disjointed events and independent events are different concepts. However, they can be mixed up quite a bit. So disjointed events are ones where they have no outcomes in common, and independent events means they impact each other. So it's slightly different, but they're really easy to get mixed up when we're looking at multiplication or addition rules. Here is the multiplication rule for independent events. So that's the key here. We're going to talk about dependent events in the next section in 5.4. So the multiplication rules for independent events is you're basically going to take the probability of each event and multiply them together. Okay. So if I have a coin, heads is 1/2, and then I have a die with 6 sides, so the chance of me getting a 1 is 1/6. So the probability of the coin and the die is 1/2 times 1/6, or 1/12. So that would be the probability that I'm going to get heads and a 1 on the die. Those are two completely independent events because the coin has no impact on the die. So I can just multiply those two events together and get my straight answer out. If the events are independent, doesn't matter if there's 20 events or 2 events. You can just multiply them all together. The key being, though, is, again, they have to be independent of each other. All right, let's look at a couple examples. So the probability that a randomly selected 24-year-old will survive the year is 0.9986. So a very high percentage, right? 99.86% chance that a 24-year-old male is going to survive the year. So nothing crazy there. However, when we start to look at growing that value out and looking at a higher thing, we can start to see some interesting things come up. So what's the probability that 3 randomly selected 24-year-old males will survive the year? Now, these 3 are all independent events. So when we're looking at it, each individual male is independent. They don't have any impact on each other. So we can look at these and just multiply them. So pull up the scientific calculator here so we can actually do this out. So I'm going to take that probability and I'm going to multiply it 3 times. So 0.9986 times 0.9986 times 0.9986. So we get the probability is, for that first one, is 0.9958. So we can see right away that the probability of 1 is 0.9986. The probability that I'm going to select 3, that probability goes down. So now let's look at if we want to do 20 of them. Now, we can sit here and do this out 20 times. However, remember from your algebra days, we have something that does repeated multiplication. It's the exponent. So we can do 0.9986 and just raise it to the 20th power. And that's going to give me the probability of it occurring, me picking 20 of them. So now you can start to see that probability is going down. So now we're only at about 97%. Because I'm looking to pick 20 people, or 20 randomly selected 24-year-old males. So what's the probability that at least one male out of 1,000 will die during the course of the year? So now we can sit there and go, okay, well, I have 1 or 2 or 3 or 4. It's like, because it's at least 1, so it's anything higher than that. However, remember from class on Tuesday, we talked about the corresponding, or the opposite, okay? So when we're looking at it that way, we can actually take it and go 1 minus that. So if we have the less than, at least, so at least 1 male, that's that way. So if I look the other direction, the only option is 0. So what is the probability that no male will die out of 1,000? So in that way, we can look at it as my probability again. So we can take that 0.9986, and this time raise it to 1,000. So 0.9986 raised to 1,000. Now this probability right here is 0.2464. So if I did 1 minus that, I would get 0.7536. So the probability that at least 1 male out of 1,000 would die during the course of the year is 75%. So that's how we can start to look at how we can use the opposite value to actually come up and help me figure out my answer without having to sit there and do out all the possible combinations. That concept is going to help you a ton going forward when we're starting to look at some more of the complex probabilities, because if you have to look at a bunch of different options to get it, you get bogged down in a bunch of calculations. Sometimes doing it the opposite direction will make those calculations, you only have to do a few of them, and then we just subtract that answer from 1. All right, here's a few of the rules that we have. Actually, make this a little bit bigger. So this is basically a summary of the rules that we covered last week and this week. So the probability of an event, remember, it has to be between 0 and 1. Okay, so we can never have anything negative, and it can never be greater than 1. Remember, 0 means that nothing happens, it'll never happen, and 1 means it always happens. The sum of the probabilities always has to equal 1. So if you add all up, it has to equal 1. We have the, when we're looking at right here, this is the general rule of addition. Remember, that rule will work even if they were disjointed, because if they're disjointed, that minus part will be 0. So that's not an issue at all. We have the complement rule that we just used a minute ago. And then if they're independent events and we're looking for the and, notice the big difference. Notice here, this is actually a big piece. That's the or. So typically when we're looking at ands, or when we're looking at addition, it's going to be the ors. If we're looking at or multiplication, that'll be the and. Okay, so when we're looking at or and ands, those are the two different ways we can look at things. Okay. Nice thing is, this is a video recording, so you can pause me to write the stuff down on the screen. If you have any questions on any of the stuff that we're going over, you can wait till Thursday and ask, or you can just send me a quick email and ask me that way too. I'll gladly respond to those, or you can even text me and I can go over that as well. All right, the next set of problems that we're going to look at is when there is actually overlap. So they are not independent events. They depend on each other. So what this is it's known as conditional probability. So you see that P and then there's the F with that line in between it. It's read as the probability of event F given event E. So we already know event E has happened. And now what's the probability of event F happening? And that's the probability that event F is going to happen given that the other event has happened. So when we're looking at this, the formula is going to look a little crazy, but then when we start to actually do the problems, it actually becomes a little bit simpler. So this is the conditional probability rule. You'll notice there are two rules here. I actually typically will end up looking more at the second one here. So we just look at the number there over the actual number. The probabilities, why it works is the probabilities are always going to be divided by the total. So therefore, those basically cancel each other out. So it's really just the top numbers that we're looking at. Okay, so it's the number that fits that value and then the number for the original E value. And again, when we actually do a problem in a minute, you're going to actually, it'll make a lot more sense. All right, so if we look at this one, we're going to compute the probability that a random selected individual has never married, given the individual is male. So when we're looking at this problem, this is the probability of never married given male. Okay. So remember the formula was the number of never married and male over the number of male. This is the biggest difference right here. Normally, we look at the bottom as the total. So, and Thursday when we did it, we looked at that bottom as the 271.7. However, in this case, it's going to look at whatever the second piece is. So the given male, so we're going to look at that 133.6 as my number down the bottom, because I'm looking at that male as that option there. So in this case, the probability is going to be the number of never married and male, which is 49.5, over the total male, which is the 133.6. So that's what I was meaning by we're just taking the numbers. Because if we look at the top here, this problem would have been 49.5 out of the 271.7. And the number of males would have been 133.6 out of the 271.7. And then those 271.7s would have canceled out. So it gives us back that original value there. So that's why it's just easier just to look at the actual numbers for the top and the bottom. The only time you're going to have to do that other piece is if they give you the percentages or the probabilities in the problem, and then you plug them into the actual formula. But in most situations when you're doing it, you're going to have the data, so you're going to be able to actually just do the calculations like this. Compute the probability that a random selected individual is male, given that they've never been married. So now you notice this one sounds very similar to the one we just did. However, this one actually is different. So this is the probability that they're male given that they're never married. So the 49.5 is still going to be my top number because it's the male and never married. So that is still the 49.5. The difference is the bottom. This is now never married and not male. So now that bottom is going to be the 92.7. Because now I'm given that they are never married. So that's a different piece that I'm going to be given. And I want to know what's the probability that a male is going to be picked out of that group. And that's that 49.5 out of that 92.7. So when you're looking at these, a lot of times in multiplication, we think order doesn't matter. And actually, in the last section, we're looking at just independent events. Order didn't matter. We could have multiplied it any way we wanted and done it any way we wanted. However, in this one, because we're looking at that given piece, order matters. So male and given never married is different than never married given male. Okay, so you really have to be careful on how they're wording the things to make sure you pick the right direction. That's why I said in class, English is the biggest problem with these, because if you read quickly through a problem, you might miss order or you might miss a number somewhere, and that's going to mess you up when you're actually doing out the problems. All right, let's look at another problem. It's a little bigger. So suppose 12.7 of all births are preterm. Gestation period of pregnancy is less than 37 weeks. Also, 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given the baby is preterm? So now when we're looking at these, this is where that probability is going to come out. So we're looking at this situation. We want the probability of normal weight, we'll call it, given their preterm. So this is the probability of normal weight and preterm over the probability of preterm. Since they're giving them as the percentages, I'm going to use the probability there instead of the actual calculation. However, the end result is exactly the same thing. The top one is going to be the 0.22%, which actually I'm going to write this as so 0.22% is 0.0022. Remember, 2 decimal places. And the 12.7%, which is the probability of preterm, is 0.127. Now we can divide those. So we have 0.0022 divided by 0.127. And we get 0.017 or 1.7%. Okay. The general multiplication rule is this. So notice the one we did before was when they were independent events. Just like when we did addition, when we're looking at the general one, we add a little extra piece because we have to take care of that fact if they are not independent. So in this situation, the probability of E and A is the probability of E occurring times the probability of F given E. Now, if they are completely independent events, it won't matter because it's going to be the probability of E times the probability of F. Because there's no connection between the two events. However, as we saw in the last example, there are situations where they are there is overlap in that situation. Now, this one's a little harder to expand out to multiple events. So we typically tend to do these at 2 at a time. And then if you have more, you'd actually just take that one and then multiply it by the next set of them. All right, let's look at a problem that goes along with this. So the probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that she or he was pulled over, is 0.9. So what is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? So the first situation, so my event E, is pulled over. And I know the probability of that is 0.8. Now, F is getting a ticket. And I know the probability of that, given that they have been pulled over, is 0.9. Okay. So these are related because obviously you can't get a ticket if you didn't get pulled over. So there is a connection between these two events. And based on the data, I know that if you get pulled over, there's a 90% chance that you're going to get a ticket. So now, what is the probability that a random select driver who is speeding gets pulled over and gets a ticket? So now we do that general multiplication rule because we want to know F for E and F. So it's the probability of E, which is 0.8, times the probability of F given E, which is 0.9. So it's 0.72. Okay. All right. That's basically all the rules and stuff we need to go over for class today. Any questions, feel